Hello viewers, I am Praveen. In this course, you will quickly learn all the operating system concepts uniquely through question and answer sessions. So let's begin. Explain fundamental state transition of processes and compare process with threads. Now, if there are four processes A, B, C, and D, and if you are using a processor with a single CPU or a single core processor, then a single core processor will have only one program counter. So every CPU will have only one program counter, and you can only execute only one program at a time. So only one program active at any instance on a one program counter or a single core processor. So if it is a single core processor, then we will have to execute something similar like this. That is, you will execute the process A first and then maybe process B, and after that you will execute process C, and then you will execute process D. And if you have a processor with a 4 core or where 4 CPUs are inside, then the 4 CPU will have 4 program counter and all of them can be executed simultaneously, something like this. Now, assuming you are actually working on a single core processor, and on a single core processor, the execution timing diagram is going to be something of this kind. So what it would do is, it will first give process A for execution. It will execute for some time, then it will stop process A, and then it will execute for some time process B, then it will stop process B, and then it will execute for some time process C, and then it will stop process C, and then it will execute process D, and after that again it will start executing process A, process B, process C, and process D, and so on. So it will execute all of them one by one. Now how this whole transition happens, let's look into that more details. So in earlier video I have already explained to you this one. Let me again do in more detail. Now once a process is created, so it is put into the ready queue. In the ready queue, this is a queue. It's something like a queue. Whenever we stand in a queue, whoever is in front will get will complete basically so it is last in, it's a first in first out. So whoever gets into the queue first will come out first. So everything that goes into the queue will actually come out from this end. Now that is given to the CPU for execution. So this both are similar basically. So here the creation, and this is basically the creation. It's a ready queue and this is the ready. And this dispatch is something what is given for execution in the CPU, and that CPU and the running is same. So once the CPU start executing it, and as we have seen in the earlier timing diagram, it will execute the process A for some time, and after that it will stop process A. So it's swapped out and again put to the back of the queue. So now the front of the queue will be B process. So B will go for execution, and B will also get executed for some time. Then that is being swapped out and it is put to the back of the process, and process C will go for execution. Now this will continue, and in case of process D, which is going to get executed, in case it has some IO operations to be done, then that will be put into the blocked queue. That is IO waiting queue, which is called as a blocked here. So for the IO operation to be done, so what it does in the meantime is it will put the next process, again process A here, for execution. So it will go on till this comes back, and once the IO operation is completed for the process D, that will again be put back into the ready queue. So this is process creation, this is ready queue, this is running, that is execution, and this is termination. In case one of the process has completed a task, whatever it has to execute, that will be ended. So this is a state diagrams of the process. Now, what are the conditions in which a process will get created? So some of the conditions when a process can get created is the system initialization. There is an init process there has to be one process which will start on its own, and that is the init process which starts on its own. The init process creates so many process of it will create many process, that is execution of process creation system. So the init process will create so many process in the OS. User requests to create a new. So whenever you have compiled some program and you want to execute, or any process that you want to run your notepad, or you want to run a PowerPoint, then all those are actually the processes, and so user requests to create a process. So when user request, if you are running any program 4 times, so you have a C program, or if you have a notepad and you are running the same notepad for 4 times, it becomes 4 process. You should know that. So user process to create a new process. Then initiation of a batch process. So there is a program that you have written which will actually create so many processes, that is it's a batch process, initiation of a batch process. So these are some of the events that causes a process creation. Now, what are the reasons for the process terminations? Some of the conditions or some of the reasons for process termination is, normally if the process is something, it has completed its work and it is closing, so it's a normal process exit. Now there could be there is something like the process has landed into an error, and because of it you have terminated the program, which is an error exit. There is also a chances that there is an error in the program and the program has terminated itself. Okay, then it's a fatal error. There is a chances that you have either the process, for some reason you have killed the process, or there is a program which is killing this process. That there could be many reasons, and or the program that you have written actually want to kill the process and create the process again, or there could be many reasons. So killed by another process, that can also be one of the reasons. Now this is again the same state machine diagram, but here we have 2 more extra states, that is swapped out and blocked, swapped out and waiting. So let us look at this process state diagram. So here again, and when the process gets created, it again comes to this waiting queue. This is the ready queue, and it is given from the queue, it is given for execution, scheduled. And once the timeout is over, it will be either brought back to the ready queue, or in case if there is some IO operations to happen, then it will be in the blocked state. Now, whenever it is in the block state, if there is an IO operation to be happen, there are chances that if there are many processes to be run, it could be moved, as it is not currently being used, it could be returned to the hard disk. That is, so if this green portion is basically the virtual memory, or the memory hard disk memory, and this yellow portion is basically a main memory. So this is a secondary memory, basically a virtual memory, where the programs will get moved whenever they are not active. They can be swapped outside, and whenever again the IO operation is got completed, they will be swapped back into the main memory. Now after that, like there are also just some chances that whereas some process is waiting here, even in then, if it's not really active, then that can be swapped out, and that could be waiting in the secondary memory, and whenever it becomes active, that can again be copied back to the ready queue and given for execution. So this is having 2 extra states, that is swapped out due to waiting and swapped out due to blocked. So swapped out is means moving from main memory to the secondary memory. But whenever it has to be executed, the CPU will only interact with the main memory. So whenever the program has to be executed, it has to be swapped back to the main memory. Now coming to the threads, a thread are part of the process. So you've seen what is a process, but a thread is just a part of the process. It's one of the it is a part of the process. That is, a process may contain one or more thread. So when a process is not containing any thread, then also it is one thread. Basically the process which is running, it's one thread. A process may contain one or more thread, but a thread cannot contain a process. So again, a thread itself cannot have a process. A process can have many threads. Now let us look at this diagram here. Look at the picture over here, and you can see that the process 1 is having one thread. It means no thread actually. So it's one thread, and so if there is no thread also, it is actually one thread is running kind of a. So if the process 1 here, another thread, and process 1. So these are all three programs that are running. And they all have only one thread. So three processes, each with one thread, and there is one more process over here. This is having three threads inside. So you can have many threads, 5 thread, 10 thread, 20 thread, based on what your program is. So your process could have any number of thread, or it could have no thread at all, or only one thread. That is, no thread is nothing but one thread. Now another pictorial diagram. There is one process 1, it is having 3 thread. The process 2, this is again having 3 thread. Process 3, that is again having 3 thread, and so on. Now, per process items and per thread items. So what are the things that are there per process and per thread? Now, a thread is a part of the process. That is what we will have to understand. It's a thread is a part of the process. So, and a thread there can be many threads in a process. So there are many things that are common to the process itself, and thread need not have that. Like there is a global variables. The per process items, the address space, the space given for the program execution is a fixed for the process, basically address space. So that the same address space is used by all the threads of that particular process. The global variables, whatever global variables are declared for that process, are visible in all the threads that are running in that particular process. All the open files can be used by all the threads of the process. The child process of the process can also be used by all the threads of the processes. The pending alarms, signals and signal handles, accounting information, all these things are only one for the process, and they are not repeated for each thread. But whereas the program counter is for each process will have its own program counter, and it will have all it is the registers details of and the stack also for each thread will have its own stack data, and each thread will have its own state information basically. So here there is another picture which shows about the stack, that each thread, there is thread 1, thread 2, thread 3. These are all inside one process. Okay, this is a kernel, this is an OS. So there is one process which is having 3 threads, but thread 1 is having its own stack. Thread 3 is also having its own stack. Thread 2, which is the main thread, which is naturally using the global variables of all the so global variables are visible for all the threads basically. It's not that it's only for 1 and 3 or only for 2. It's for 1, 2, 3. All of them have a global variable. So each thread has its own stack. Now here there is one example how you can utilize a thread program. So if you have one program running and it's a word processor program, so you could have one thread running to understand the keyboard. So whenever we are entering the key, one could be only listening at the keyboard. So whenever the key is pressed, it will be able to take the character and display. There can be another thread running for the display of that particular the word processor file itself, and there could be a third process running which will save this particular information to the disk. So like this you can segregate the work based on the different work. Like if you are having a socket program, and if you are having some program which will take information from one end and send it information on another end, you can have two thread, one which will actually accept data from one end and the other one which will send data on the other end. So it's something you can divide the whole process, your whole program, into threads like this, and they all will work simultaneously. Basically they are all, as you know, that they have to be scheduled, but those threads will work like this. Now another pictorial diagram over here to show you that how this particular how they are there. So the register, counter and stack, they are all common for all the this is a single thread, so it will have its own register, counter, stack, it will have its own data, its files and code. Because it's single thread, everything it will have its own. But if it is a multi-threaded application, the thread will have its own code, but then the data is going to be, the data segment will be shared by all these three threads. Okay, the open files can be shared by all the three threads, but they will have the stack segment. Each thread will have its own stack segment, it will have its own program counter, and it can have its own registers. So each thread can have its own stack, program counter and register. So here the difference between process and thread. Process is heavyweight or resource intensive. So a process is, as we have seen, it's a heavyweight. It needs a lot of information. Okay, and so it's a heavyweight. Whereas a thread runs inside the process and naturally it does not require a lot of information. So thread is a lightweight, takes lesser resources than a process. Process switching needs interaction with the operating system. So if you are running from one process to the other, and from next process to the process switching will require interaction with the operating system. Thread switching does not need interaction with the operating system. The thread can be independently managed inside the process itself. So the user actually can schedule how the thread has to be run. So that can be written inside his own program. If it is having four threads running, then he can schedule each thread how he wants, or he could run all of them. So it's based on the programmer. The process, it can be written inside the process, and the operating system need not know how these threads are scheduled. So thread switching does not need to interact with the operating system. In multiple processing environment, each process executes the same code but has its own memory and file resources. So in multiprocessing environment, each process executes the same code but has its own. Now, as I told you, you could have the same. If you have a notepad and you could run 4 times the same notepad, or you have your own program and you can run that same program 4 times. But if you run your own program 4 times, it will have each time the new process is getting created, and each time the new process will have it will have its own memory and its file resources. So all the information of that particular process will be separate from the other process. Okay, though it may have the same code itself. All thread will share the same set of open files and child processes. So if you have 4 threads running in one process, then all the thread will share the same set of open files, whichever are opened by the parent process and child processes. All of them can use the same share the information. If one process is blocked, then no other process can execute until the first process is unblocked. So to tell you, if one of the process is blocked, if one of the process is basically blocked, then that particular process cannot be executed, or it cannot be it has to unblock itself, and it will the other process cannot execute that particular process. But in a multi-threaded environment, if one of the thread is blocked, there are other threads which can still keep running basically. So the program may be working, and it is possible that, like, based on the condition in which it has been, like, if one of the thread has blocked the other thread, then it can even open the other thread, and so on. In multiple processes, without using threads, use more resources. Multiple processes without using threads use more processes. Multiple threaded processes use fewer resources. So if multiple processes are running and they are not having multiple threads, then they are using more resources, because each time a process is created, as we just discussed, the code segment and the data segment, everything is going to be having its own resources, file resources. If the whole setup is going to be, the process setup has to be created for each process. So if there are multiple processes without using threads, then use more resources, whereas multiple threaded processes use fewer resources, as it's using the same code segment, the same data segment, it will use a fewer resources. In multiple processes, each process operates independently of the other. So in the multiple processes, each process operates independently of other. In one thread can read, write, or change other threads' data. So in a multi-threaded environment, there can be an interaction between the thread, and one thread can read and write or change the data of the other thread. So I hope you understood this very clearly, and if you have liked this, please subscribe, like, share, and comment. Thank you for watching.